D.1, introduction to Fibonacci numbers. Yeah. So it's a very famous problem. Yeah. And there are many ways to calculate Fibonacci numbers. Yeah. Our problem 10, calculate Fibonacci numbers. First, definition. Yeah. Many of you may already know it. Yeah. Here, I just recall, given recursion formula. The recursion formula is very simple. The base case is two base cases, f0 equals 0, f1 equals 1. The recursion formula fn equals fn minus 1 plus fn minus 2. That simple recursion formula. But the numbers generated, we call Fibonacci numbers. They have so many interesting properties. Yeah. And I remember there is some book, the whole book, talking about all the advanced properties of Fibonacci numbers. Some properties, very complicated, very hard to prove. Yeah. All right. Here, our problem, we need to find Fibonacci numbers f sub n efficiently. There are many ways we can find Fibonacci numbers. And we want to find some fast way for the Fibonacci numbers, yeah, given n. Given that capital N, problem size, we need to find f sub n. Yeah. All right. Here I list first a few Fibonacci numbers. Yeah. So you can see, yeah, it is not easy to find some simple rules. Yeah. The pattern, yeah. Can you see any pattern? Yeah. It's hard to see any obvious pattern here. Yeah. All right. Yeah, the reference in our textbook, section 2.5, page 80. Our plan, yeah. Yeah. Because we need to learn some interesting properties. Yeah. So we make our plan. Yeah. The first time we solve it algorithmically. Yeah. So we use computer algorithms to solve this problem the first time. Yeah, but the second time, yeah, so that's the, write a computer program to implement some algorithm. Yeah, that's first way. Second way is solve it mathematically. Yeah. Because if we can find a math formula, then using the math formula usually much faster than without formula. We have to implement it using some computer algorithm that most of the time, algorithmic way won't be as fast as the formula way. Yeah. So for that reason, if it's possible, we try to find a formula for it. Yeah. For this example, yeah, we can find. Although we need to do a lot of work, but we can find that formula, yeah. Derive a math formula. Yeah. All right. Then there is a simple implementation. Recursive function. We create a recursive function, integer Fibo, and that's the problem size, and two base cases, these two base cases. Then after that, just recursion. Yeah. So you can see this implementation is so simple. Yeah. But the problem, although it is simple, how fast it is. We need to consider the efficiency of this algorithm. Yeah. This recursive algorithm. Yeah. it solves the problem correctly. Yeah. So the answer generated by this function is correct. Okay, yeah. But the question, is it a good implementation? Yeah, we need to think about it. We need to do some analysis or do some experiments. Sometimes we need to do experiments. Is it good? Yeah, the answer, it's a horrible implementation because extremely slow. Yeah, why I use this, strong word, horrible, extremely slow. Yeah, because its growth function, I mean the growth function of the algorithm, its growth function is an exponential function. Okay, exponential function, something like a to the nth, a greater than 1, like that. That's what I mean horrible, extremely slow. Okay, yeah, we will see that. So why its growth function is an exponential function. Yeah, we will see that later. Yeah, all right. But we want to understand why it is so slow, right? Yeah. So here in this slide, I want to explain why our first implementation is so slow. Yeah. Let me draw a recursion tree. Yeah. To show you the reason. Yeah. I just calculate Fibonacci of 6. That's a small number. Fibonacci number for n equals 6. Yeah. For this small number, if we use that recursive function, look at what is the recursion tree we need to draw. Yeah. Let's do one by one. In order to find Fibonacci of 6, we need to find Fibonacci of 5 and a Fibonacci of 4 first. All right. Then, in order to find Fibonacci of 5, we need to find the values for Fibonacci of 4 and Fibonacci of 3. Yeah. This side, Fibonacci of 3, Fibonacci of 2. All right. So then, keep doing. We need to get all the values when we reach the bottom. The bottom means we need to use the value of Fibonacci of 1, Fibonacci of 0. They are the base cases. Okay? After we apply the base cases, we can get values of all those Fibonacci numbers. Yeah. And then we can backtrack to get to the root of this recursion tree, and we find the value of Fibonacci of 6. We use this tree to interpret, to explain the details of that recursion implementation. Okay? Can you see any obvious property from this tree, recursion tree? What's wrong here in this recursion tree? Can you see something not quite right in this tree? Yeah. All right. Yeah. Yeah. Let me show you. Yeah. Observation. Look at Fibonacci of 2. How many times do we need to calculate Fibonacci of 2? You can see 5 times, right? In order to calculate Fibonacci of 6, based on the recursion, we need to calculate Fibonacci of 2. This same number we need to calculate 5 times. Okay, yeah. 5 times. Is it necessary? The same number, why you calculate 5 times? We only need 1 time, right? We only need to calculate 1 time, not 5 times. Okay? But we did 4 redundant times calculation. After the first one, the remaining 4 times calculation all redundant. We should not do the redundant calculation. Yeah. Then you can imagine when the Fibo number is big, yeah, not too big. Here, I just consider Fibo of 100. Can you imagine how big is the tree? Yeah. If the root is Fibo of 100, the recursion tree is very big. Yeah. Nobody can draw this full tree. Right? Yeah. And if you imagine how many times do you need to calculate some smaller Fibonacci numbers in this recursion tree, large number, right? That's the reason this implementation is extremely slow. Yeah. All right. And if you do experiment, extremely slow. Okay, yeah. So that I make it our second programming project. Let you feel about it. Let you feel, how slow it is using this direct recursion way. Yeah. And actually, you cannot do Fibo of 100. Okay, if you do Fibo of 100 using the long integer type, you get overflow. Okay. Even the long integer is not big enough to represent Fibo of 100. Think about that, how large it is. Okay, yeah. All right. So you will see it in our second project. Okay, yeah. All right. The problem, too much redundant calculation. That's the reason it is bad. How to improve it? Yeah. If you know the reason, then the idea to improve it, remove the redundant calculation. Just remove the redundant calculation. All right, yeah. How to remove? Yeah, that's next question. First, we know we need to do redundancy removal to improve the efficiency of this algorithm. Yeah. The next question, how to remove, how to avoid redundant calculation. Yeah. How to improve method 1, yeah. Iterative algorithm. Yeah. We do not use recursion, yeah, because that recursive algorithm gives us the huge redundancy. Yeah. If we do not use the recursion, then we can avoid it. Yeah. And here we can use this iterative method. F of 0, so we create an F array. F of 0 equals 0, F of 1 equals 1, then we calculate the array elements okay, one by one. Yeah. From 2 through n, but every time we just do one addition. We just do one addition. We know using computer, addition is very fast, right? Addition is extremely fast. And this method, no redundancy. You can see each F number we only calculate once, no redundancy. No redundancy, right? Yeah, that's good. The result, very fast. How fast? How fast? I can give you an idea if I use the asymptotic notation. Now, we use asymptotic notation. Big theta of n. Yeah. Big theta of n. Yeah. How fast it is? C multiple times n. C some constant times n. Okay, yeah. C times n. Comparing the previous recursive implementation, exponential function with a greater than 1. How big is the difference? Okay, yeah. So this is our first way to avoid redundancy. Okay, all right. Second method, this one, we keep that recursive algorithm. Yeah. But we do some modification. If we can avoid redundant computation, we can still keep that recursive algorithm. Yeah. So you may wonder why we still keep recursive algorithm. So we know recursion idea is very powerful. Sometimes we need the power of recursion, right? Yeah. So last time I showed you the Tower of Hanoi problem. We need the power of the recursion. So we don't want to throw away the power of recursion. Okay? Yeah. So for that reason, we just do some simple modification to avoid redundant computation. Yeah. Here, let me show you how to avoid it. Yeah. The modification is very simple. Yeah. All right. Use an array to store calculated values. Our goal, our principle, we only want to calculate each Fibonacci number once. So that is our principle. Okay, yeah. So how to avoid more than once calculation? Yeah, so the method is this one. Use an array to store calculated values. The next time when you need to calculate that value again, because you already have it stored in your array, why you need to calculate another time? Yeah. That's the idea, simple idea to avoid redundant calculation. Yeah. Make sure that no value is calculated more than once. Yeah. You only need to check your array if you have already stored that value or not. If that value is not stored in the array, then you need to calculate it. That's the first time you calculate it. But if you find there is a non-zero value already there, that means you have the value already. So you just retrieve the value from the array. Do not do recalculation. So that's the basic idea of this second method. Yeah. The second method has a fancy name called dynamic programming technique. It's the topic in our chapter 8. Yeah. For this class, I do not have time to talk about dynamic programming, But here, using the Fibonacci number, I give you a short introduction to the dynamic programming idea. Yeah. All right. The essence of this method, yeah. No repeated calculation with this method, store calculated values. Yeah, that's the essence of the dynamic programming. Okay, yeah, all right. Yeah, here, let me implement method 2. Yeah, implement that idea. Yeah, because you may ask me how to store calculated values. Yeah, here, I show you. Yeah. Yeah. And this method is also called a dictionary method. Yeah. Why we call it dictionary method? Because we use the array we use an array as a dictionary. Why dictionary? Because we need to look up for some number, calculated number, lookup. Okay? Lookup. Here, lookup for what? For that Fibonacci number, for a Fibo number. Right? Yeah. After we find one Fibonacci number, we store it in a dictionary. We call it dictionary because later we need to look up for one particular Fibonacci number in it. Yeah. So that's the reason dictionary method. Yeah. All right. So the property, yeah. Recursive algorithm without redundant computation. So the dynamic programming, when we use the dynamic programming technique, we use the recursive algorithm, but we find that we use the dictionary method, we can avoid redundant computation. Yeah. Use an array to store calculated value. So that's the dictionary that we're talking about. Yeah. Make sure that no value is calculated more than once, because we need to check if a requested value is already calculated in our dictionary. Yeah. So that's the basic idea. Yeah. Now our implementation is like this. Yeah. We create an array called a known F array. Known. The values are known. Yeah. After you store Fibonacci numbers in this array, they are known. Since they are known, we should not calculate them second time. Yeah, that's the meaning. Okay, all right. Then checking step. How do you check if a Fibonacci number is known or not? You check the condition. No known f of I is greater than 0. Yeah, because when you do initialization, you initialize all the values in this array 0. Yeah. But after you assign it a positive Fibonacci number integer, yeah, this is assignment. Assign S you calculated, because S you get from here. S you can assign to the known value, but you only need to assign it once. The next time, after you assign one Fibonacci number to one position in this value, it becomes positive, right? So the next time, you can return that value directly. You do not need to recalculate it. Yeah. So this way, this condition check, you guarantee each value, Fibonacci value, is only calculated once. Yeah. So that's the first line, has that property. Okay. After that, two base cases, then still we keep the original recursion. Original recursion we only use when that value is unknown. The Fibonacci number for that size n is unknown. Then we call the recursion. Yeah. But when we call the recursion, this recursive function may need to use the dictionary to return the known values. Yeah. That's the way we avoid redundant calculation. Because these two numbers, very likely these two numbers both come from the dictionary. Okay? Not from repeated calculation, from the dictionary directly. Yeah. So that's the reason we can save time. Okay? Yeah. So if you implement this algorithm, the efficiency still big theta of n. Okay? You can see very good. Yeah. Although a little slower than method one. Yeah, method one iterative should be a little faster than this one. Yeah, because this one you use the recursion, right? Recursion way, usually we need to use more resource. The stack could be deep, right? Yeah, so we use more resource than our method number one. So method number one should be a little faster than method number two. Yeah. Yeah. But we still, because method number two, we keep the power of recursion. For this problem, because it's simple, so we may not need the power of recursion, but for the general real world problems, we cannot avoid recursion. Yeah. Because the power is much bigger than the extra resource it is used. Yeah. All right.